Right. Well, thank you very much for coming back. And I think it's part of my job here to make this information architecture as exciting as possible to help you wake up and enjoy your ice cream. So this artificial intelligence thing is really all about automation, predictions, and optimization. And these are sort of gift-wrapped in today's hype cycle called AI, and I think that's fantastic. But when you look back over what firms like IBM have been doing, starting off with the lunar landing 50 years ago, walking around on the moon and then flying back. I mean, the code that was written by some IBM guys at that point was around automation of switchgear and then trying to optimize it to make sure it worked and they came home safely. So 50 years ago, assembler code was being written that does exactly what AI claims to do today. Things have moved on a little bit in that we can take on perhaps tougher challenges that push computers to the absolute boundaries of possibilities. So I'm going to run through some examples of those briefly. The bullet train in China, optimized for airflow, fluid dynamics, takes a lot of computing to come up with the shape that turns out, by coincidence, is exactly the same shape as the beak of the little kingfisher bird. So nature has been doing these things for longer than we have. IBM invented the barcode. That's nice because that optimizes your experience in a retail store. We've managed to decode the genetic makeup of the cocoa bean, and the benefit of that is it optimizes the relationship I have with my girlfriend when I give her a bar of chocolate. The stuff tastes better now. We're now doing more work on atomic optimization. So you see the little blue dots on the corner there, the little blue dots spelling out IBM. Those are individual carbon atoms. There's two miracles going on here. One of them is that if we can arrange 8 atoms in a stable environment that will stay the same for a long period of time, and one of my customers asked if we could do it for 100 years, but stable for a long time, we can define a 0 or a 1 in a tiny space. Currently, on the world's best computing environment, we're using about 100 atoms to save 1 byte of data. So if we can do it in 10 or less, we can shrink the size of these computers by a factor of 10. That's pretty good. But that is the limit. We can't make it any smaller unless we change the game and do something quite different. So hence the arrival of things like quantum computers and new maths. So although things like fractals have been around for a long time, we can now do pattern analysis that results in things like MRI scanning, another IBM invention, which can actually save lives. That's an optimizing technology if there ever was one. We've managed to get the barcode to evolve into something electronic, of course, and it was an IBM guy who was tasked with the challenge of getting a magnetic stripe to stick to a bank card. And he came home from work one evening after a long day in IBM and saw his wife was actually ironing and figured it out from there. So many of the advancements in technology have been driven out through very practical engagements. The net result is that this AI thing, these 3 key words, automation, predictions, and optimization, have a forecast value of 16 trillion euros to the global economy by the time I retire, which hopefully will be in, 10, 12 years' time or something. So a massive amount of money is predicted to be extracted from these capabilities. The little car thing in the corner there is one of my favorite projects. We've got 8.5 million BMWs driving around Germany, sending us their connected car data with the driver's consent. And we're now optimizing things like engineering, driver experience, and predicting which parts need to be replaced to overall improve the driver safety and experience. So these are things that are actually happening for real. So the key messages from this is that you can't do this kind of AI unless you've got the right information architecture. And I'm going to run through the elements of that as quickly as I can, because it's a pretty tough subject. And there's a lot of reading material I can introduce you to. If you really want to go into detail, we can do that offline. But the good news is there are shortcuts, and better than that, it's amazing when you get it right. So the most part of this presentation will be the easy stuff to listen to, because these are the stimulating, hopefully exciting examples of things that we've managed to do, taking this approach with an information architecture that supports advanced AI. So let's have a little step back for a moment and think, well, what is the problem we're trying to solve? It's simple. It's complexity in many ways. One of them is the definition of AI itself. You'll see a chart here naming various AI components, and through the lectures I've listened to this morning, it shows that even within each of these, there are subcomponents of increasing complexity. This is the most complex compute environment I've seen ever, and I've been in this for most of my life now. And then to support this, we have this data requirement problem. To feed each of those capabilities, we have, well, we call it the ladder in IBM. We have to collect, organize, to analyze, and infuse, meaning we embed the AI as close as we can to the point where it delivers value. And each of those steps are, data management problems, really. So we have a lot to do. Now, this is fighting for the attention of the world, who are now distracted by things like move all of your applications to cloud, data safety, or GDPR, and so on. So this big red number here, 81% of companies do not yet understand the data required for AI. So my mission today is try and get that a little bit nearer 80%. Hopefully we can do that. Let's have a little bit more about the complexity. One of the dimensions of complexity of AI and this architecture is the flow of data. So we start off over here with years worth of data in many different legacy formats, none of it compatible, all of it's just been around for a long time, will be there for a long period of time. But the key thing is it's years of data. And it does take months to get your head around how to prepare it for a new business use. When we actually go into the training phase, it can take weeks to get things done. We can use advanced computer techniques to run the model cyclically in minutes, but it still takes weeks to actually get it done as a business. And what we're trying to achieve here is something that when someone is using the application, it works in seconds. That gives us a new problem. Once we have data on the interaction with AI, there's a feedback loop. Has to go back into the beginning, and that's one of the best data sources that you'll ever see as a data scientist is the human interaction with AI, and it allows you to evolve the use of the application to make it much more customer friendly. So that's a primary advantage, but it's super complex to do. Now, another complexity dimension is all the people. So we start off with a very clear brief from a business sponsor who gives us a budget and authority and shows us, how it aligns with his strategy to sell more or save money, and then we hire a bunch of people. All of them are gifted individuals. All of them have their own role to play as a team. It's a team sport, but each of them have their own opinion, and those things sometimes don't work very easily. So we have to find new ways to collaborate as humans to actually get this thing built. Okay, so this is probably the hardest bit, and I'll try and make it the shortest bit, but the infrastructure reference architecture, and as I said, there's plenty we publish on this stuff. If you don't use IBM Redbooks as a free source of good thought-out information, then I'd suggest giving it a try, because these things are good reading. They're not necessarily plugs for IBM products, but they show you how architectures can work. And the three most important things of this linear architecture here is the initial sponsorship. We always start small. Sometimes for free, sometimes tiny amounts of money, tiny amounts of time being used with one or two boxes to actually prove some sort of concept. And that doesn't actually win trust by itself, but the moment we expose it to customers, we try and get that win trust tick in the box. We want to get it so customers are actually engaging. And I'll come back to what that looks like in one of my examples with Stena, because at the next stage, obviously, is iteration. Having proved something works, shown it saves money or makes money for the business, we then need to stack it up, rack it up, and increase the hardware. So whilst the elements of data storage and the horizontal layers here, like Spectrum as a storage architecture, the Docker principle, all of these layers need to be there. The main thing is right from the very start, we have to design scalability into it with as much agility as possible, because we never really know what the customers are actually going to do with the system, even though we may think we do. No one ever got fired for buying something from IBM. Well, that was an advert that came out about 20 years ago, and it's still thrown at us on a daily basis as a joke most times. The thing that we've tried to do in this example is squish a lot of complex technology into a box that has the capability to run it. So on the previous slide, you saw these racks. This is perhaps what one of them could look like. The complexity here is that we have to make all of these things work together and then support them all. So we're taking away a lot of the pain of building infrastructures for AI and productizing it. The alternative, of course, is do it yourself. But I think you might find that that pressures the sort of scalability of the architecture. So the idea of this product is to help you get AI running on complex data as fast as possible. There's a fundamental weakness with it. Anyone see what it is? doesn't have your data on it, does it? And data is typically, when I go see my customers, the biggest companies in Europe, they typically say their data's in AWS or in our cloud or Azure, or actually in all of them, all at the same time. So we have a problem of disparate data. So how can that be fixed? Well, earlier this year we bought something called Red Hat. I'm sure you all know what that was, but one of the things we got with that was this OpenShift product. And this is a way of creating a management console of data across all of the different clouds. That's the top screenshot, and the bottom screenshot shows all of the objects of data that you can get at wherever they lie. So if you're building an application that relies on data from 10 different places on 10 different clouds, this is the kind of glue in the middle that you could use to get at it all and manage it all. Perhaps doesn't matter if you're building a prototype, but if you're trying to build something up that scales, somewhere in the middle, you're going to need some glue. OpenShift isn't the only product out there, but it's a good one. So take a look at that glue. Now, I'd like to go back a little bit now. The history of AI. When my oldest, my favorite daughter, I could argue, was born in 97, Gary Kasparov was beaten by an IBM team who were tasked with beating him at chess. And the first year, 96, Gary beat IBM. The second year, we'd learned something, and we beat Gary. And that was the first year where cognitive technology had surpassed human capability in a complex environment. We won the chess game. The same team were told, well done, have a bonus, now go do some AI stuff. And in 2011, the same team put this little black box called Watson up against Ken and Brad. These two guys were doing really well. One of them is a professional game show player. So the game of Jeopardy is one where a question is asked, and you have to hit the button if you know the answer, and then you have to basically gamble how much money you're sure that you'll get the answer right. And if you gamble right, and if you have good recall, you'll typically win the game. That's how Ken and Brad did. But we managed to beat them. We used 80 gigabytes of unstructured data, Wikipedia-type stuff, no internet connection, on one box. 80 gigabytes is about the same knowledge capability storage as a human brain, just roughly speaking. Not a fair comparison, perhaps, but we managed to beat them. And that was really kind of a proud moment, and Watson was born. So that was 2011. It's matured a little bit now, and I want to begin to introduce you to the kind of concepts that once you've got all of the data in one place or one machine, what you can actually do with it. So I'm going to introduce you to something called Debater. And this is, I'm going to play some video clips. They're all on YouTube. All of the links are available. So if you like some of this stuff and want to use it yourself, please do. Let me see if I can get this to play. Yep.
Real world problems, a lot of times they don't have a clear bottom line win. Otherwise, we wouldn't debate things.
According to rules set by the candidates themselves.
What we are trying to accomplish here is really to demonstrate that we can have a meaningful and valuable discussion between man and machine.
We are actually trying to show that a computer system can add, if you want, conversation or decision making by bringing facts and doing a different kind of argumentation.
Hello, Dan. Thank you for the opportunity to be here today.
The debater system tries to understand the concept over which we are debating.
Having analyzed the data, I will argue that we should subsidize music education.
When it gets the topic, until you hear the first speech, it's collecting all the possible arguments, trying to remove redundancy.
It is about recognizing important issues for society.
The system is evolving.
IBM Debater can have all the opinions in the world, but IBM Debater does not pay taxes, and we do.
You are speaking at the extremely fast rate of 218 words per minute. There is no need to hurry.
The value of the technology is really to allow decision makers to take more informed decisions. There is a territory which is uncharted to some extent, and this is where we are now.
Thank you for listening.
So, you know, sometimes you go to that expert to get some specialist advice. You're new in your job, you talk to the expert, or you have a new piece of technology, you ask some young guy how it works. We're trying to put that knowledge into a box, and it so far seems to be working. But what is it going to be like when the average person meets AI for the first time that has this human-like capability? Because none of us have used it, really. Let me show you what James thought of it.
Needs. Is that a thing? I'm just waiting here. There should be someone called Ollie coming to pick me up. Ollie?
Hello, James.
Who's that?
It's me, Ollie. Please have a seat.
Right. Where's the driver?
I'm the world's first cognitive, self-driving shuttle. And I'm electric. I'm the future of travel.
Is this your only voice? Can you do any other voices? Can you do a Tennessee accent?
Hey, y'all. Who wants grits?
I mean, honestly, I don't always trust my driving. Why would I trust a computer?
Because I don't drink, text, or get tired.
So how do you flirt with other buses if you don't text?
Ha ha ha.
Is that your laugh? Thanks so much, Ollie. Thank you.
So it took about 40 days to build that engine that has conversational and awareness knowledge. So it knows who James is, it knows the safe boundaries of a pleasant conversation, it has a sense of humor. The other half of the engine is driving the bus. That's extremely complex, but it took 40 days to build the engine that was good enough to put as the customer interface into that amazing bus. And these are actually on the streets. You'll notice an absence of traffic and people, so this product is not available for sale in anywhere other than a closed environment, a university campus, a shopping center type system. But I think this is the future of travel, and it's fun because you can ask it a lot of questions about your journey. Okay, so remember I said there were some shortcuts. Building stuff like that is pretty fun, it's pretty cool, it's great, but let's look at some easy ways into deploying AI within infrastructure that's already ready to go to save time and deliver business value faster. There's a screenshot here of something called Maximo. Asset management to industrial, capital-intensive companies is crucial. They may have thousands of robots or shops, plant, equipment, electrical circuits, Heathrow Airport, all of these moving parts. And all of those things would be stored in an asset management database. The one IBM's got is called Maximo. There are others like SAP's system. And between those two products, they kind of dominate that space of large asset management systems. What we've done is look at the database of the hierarchy of equipment and look at the database that's being fed by sensors from all of that equipment. So in the airport, all of these travelators, the elevators, all of the data from those things is going into this database. So we can begin to use it as a place to run predictive analytics. And the predictions showing here, not particularly exciting ones, are really saying, hey, there's an engine over here that's going to overheat, or there's some component here that's it's working okay now, but it's going to need some maintenance. So out of that, we can generate trouble tickets where we can identify the engineer, the part required, the prediction of how long we've got before it will fail, the prediction of how long the job should take, how much it should cost. And then the feedback loop from that will improve the serviceability of complex capital equipment. So it's pretty much standard predictions, but on a very complex data set. And it does seem to be working. And there's another one called Doors, and this is pretty obscure unless you're in the requirements management business. So guys working on the car design team for BMW, Jaguar, whatever, using this product to define the requirements for every component, every assembly, and ultimately, of course, the whole vehicle. And these components are complex. They have to be written in English language or any natural language. And they're quite complex because they're a mixture of engineering, feature function, weight specification type descriptions, quite difficult for engineers to do. What we're doing is finding that AI, because it can understand language, can actually make some recommendations, a little bit like the way that if you're using a word processor, it will underline a misspelling in red and suggest a better alternative, and oftentimes it'll underline a sentence in blue to show that the grammar can be improved. What we're now doing is the same thing with AI and saying, look, you've written a paragraph that is so complicated to understand, we suggest you break it into 3 separate paragraphs, each defining one part of the requirement. And when we add that discipline into this application, we find that it saves a vast amount of time. It means that designers who are new at the job can work at the speed of mature, experienced designers. So basically this thing, embedded AI, is accepted by everyone, just like word processing advantages. And that's pretty cool. But perhaps not as much fun as this. So we've got something called Tri-Rigor, buildings management. So the management of a building like this cinema, where there's a whole lot of moving parts to it. There's heating systems, cooling systems, light systems, all of these things, or a simple office have to be managed. And we've got a product called Tri-Rigor that happens to be in that space. That's not important. What is important is the way that we can change the interface to that to save time and have a bit of fun and introduce AI in a lively way. So I'm going to introduce you to Sarah.
Hi, Sarah.
Hello, I am your office assistant. I can help you book meeting rooms, submit service requests, provide building info, tell you about my creators, and tell jokes.
I'd like to book a room for tomorrow at 2 p.m.
Looks like the Elvis Presley room is available tomorrow at 2 p.m. Would you like to book it for 1 hour?
Yes.
Okay, I'll book the Elvis Presley room for you.
Where's the mailroom?
The mail room is located on the first floor to the right of the reception area.
There's a broken chair in this room.
Which room are you making the service request for? Please say the closest room name.
Rolling Stones.
Okay, I'll make fixture and furniture request. Anything else you'd like to mention about this request?
Yes, it's the blue one in the corner.
You said, yes, it's the blue and in the corner. Is that correct?
Yes.
Okay, I'll submit your request now.
Where can I get a coffee?
There is a restaurant just behind the main lobby which sells hot meals, snacks, and also hot and cold drinks.
Who created you?
I am built by Quantum Capture and IBM Watson IoT.
Tell me about IBM.
IBM enables clients to improve the operational efficiency of their physical assets and reduce costs through the power of IoT data and artificial intelligence.
Who is Quantum Capture?
Quantum Capture enhances customer satisfaction, engagement, and retention with virtual humans powered by AI and chatbots.
Tell me a joke.
What do you get when you cross a snowman with a vampire? Frostbite.
Thanks, Sarah. Goodbye.
Well, there's Sarah. So what we're seeing here, and that perhaps is a difficult one to put a value on, except for its convenience for the people who need to interact with room booking systems, is this kind of recognition that humans have certain skills and abilities, morals, imagination, common sense, particularly common sense, whereas cognitive systems, computers, are much better at things like pattern identification, predictions, and so on, but also developing domain expertise, as we've shown with things like the Watson Jeopardy machine. It develops expertise. So what we're seeing here, and IBM's sort of mission is to say, can we make humans operate at their most effective level by having access to really useful information in a way that AI should deliver it. And the example I show of, not to ridicule them, but let me just say, yeah, here we go. You probably won't see the screenshot terribly well, but if you just go to Google and you type in a sentence, show me something that is not an elephant, what you're going to get are 1,000, 10,000 images of elephants. So what seems to have happened with the public perception of AI is that it doesn't listen to the question. It just looks for keywords. And the human being can use common sense in a far better way. So the automotive example is easy. How fast will the car go? How fast will my car go? It'll show you in the manual the top speed, a couple of 100 kilometers an hour. But if I ask, let's say I'm supervising my young daughter who's learning to drive, and she says, Dad, how fast should I be going? It's the same question, But I could say, well, it's raining, you're a learner, it's school time, there are kids everywhere, I need you to be doing no more than 30. It's the same question, but answered in context. And that's the bit where AI becomes really useful. And to deliver that, we have to give it access to all of the data, the weather, its location, common sense, track record of driving. And it's that difference that I think really shows the value of that enterprise architecture. So I want to show you an example of a company who have really been working on this. This is one of our really effective early adopters. The Woodside operate those machines, so it's a rig out at the sea extracting gas. And the documentation from a machine like that is 5 years worth of reading, so there's no single human who's read it all. But what you have here are engineers who have to make critical decisions in time. And if they get it wrong, you could have a catastrophe. So the whole point about the way that you currently operate a machine like that is you hire expensive people, you fly them out there on a helicopter, you give them access to 38,000 documents and ask them to take the best guess as fast as they can. Now, the whole point of AI here is it shows, well, they've basically said, hey, this has saved us $10 million so far because it saves time. It gives access to the engineers to the right data as fast as they need it. So let me show you what that looks like.
I know you, friend. I know every meter, every gap, every specification. I know every metric unit of pressure imposed on your 119,000 ton frame and how it will react to the extreme conditions here on the remote northwest shelf. I know what a team of engineers in Norway reported on you and what a retired project manager documented on you a decade ago. I know fuel mixtures and flow rates, hard data and soft data. I know all this because we're designing a cognitive system with IBM Watson that consumes and learns everything written or reported about you from millions of files, decision logs, and technical evaluations spread across our company. We teach Watson to think like an engineer. Watson teaches us to think like 1,000 engineers from 1,000 different sources. I know temperatures and pressure gradients, anomalies and patterns. When you succeed, I will know why. I will know how. With Watson, we're asking more questions because we have more answers. We're making smarter decisions because we learn more every time we make one. And I know we're just getting started.
Well, I think that's pretty cool. The input data was 38,000 documents, many, many pages, and the more interesting data has been from the 400 engineers operating these machines, what actually do they want to know? And we can analyze that interaction between the man and the cognitive system, the iPad, whatever it looks like. And actually that data has become extremely useful to allow us to surface out of the 38,000 documents which are the ones that are actually most useful at a certain point, at a certain condition, and accelerating their access to that document. And that, I think, might save some lives, but it helps these guys extract gas, and that's what their business is. So, there we go. Slightly nearer than that, project I was really proud to have been responsible for over the last couple of years. Stena, the ferry company. They have a call center in Gothenburg, and you can call them up and get pricing on tickets. You can buy a ticket, and you can discuss your journey with them. The problem with Gothenburg is the labor rate's quite high, so the cost per call was actually quite a problem. And there wasn't a great willingness on the call center operators to provide a 24/7 service. So we built a bot that answers what we thought would be the standard questions to take the pressure off the call center. And 500 people started using this thing. It cost about 20,000 euros to go live, so a tiny amount of money. But then we found that the data that was the interaction between the customers and the bot became more and more interesting. Many of the customers were asking to buy a ticket. And the cost of integrating the ticketing engine to the bot was actually a lot of money, 10 times the cost of the bot. So we had to sit down and say, is it worth it? How many tickets will it sell? And work with the call center, whose job is now no longer to process ask for individual credit card numbers, but to support the customer engagement and make sure that real problems are getting solved. So there are more people in the call center, but they're being really used for their human skills, their humor, their sympathy, to actually help the customers get what they want, with most of the admin being done online. Now, the smiley icon was a bit of a fastball, because we certainly didn't expect that. But what do you do when you're talking to a call center human, and they'll say things like, well, I seem to have solved your problem, sir. Is there anything else I can help you with? And I'll say, no, thanks. I just want to go now. Thanks, bye. And they'll say, yeah, well, thank you. It was a pleasure talking with you and helping, and I'm sure there's something else we can do for you. No, I just want you to go. That doesn't happen in a bot, does it? You just send a smiley icon, I'm done, thanks, gone. So Steno are then getting hundreds, thousands now, of smileys or other emoticons, which is a natural way of concluding a conversation. So Steno had to very rapidly decide, what on earth are we going to do with that? What happens if someone sends you a smiley? What do we do? It's a marketing person's dream to have this new data source. So the whole point is that the evolution of these applications should be driven from a very small starting point, as cheap as possible, deliver some value, and then figure out how to really delight customers. So that's the iteration of that project. So hopefully you'll get to use that app, because it's quite fun, it seems to work, and ask it good questions. I want to talk to you about Mercedes for a little bit. When you buy a €100,000 car, it comes with a manual, or it used to, a book, quite a heavy read. And you'd be expected not only to look things up if you didn't know how it worked, but to fault find using it. And the problem is that most of the drivers, they didn't really know what the icons were, how to describe a problem. If you look up tire pressures in the back, it won't be there. You have to look up wheel, go to the wheel page, and then it'll refer you to the tire pressure page. So the book system just doesn't work. So we've done a project with Mercedes. It's a bit of fun. And here's a short preview of it. These are Mercedes marketing guys who are explaining how it works.
Hey, Sasha, you remember it in Geneva, during the motor show in Geneva, I talked already to you, first time ever, about the virtual assistant. So what I have is Ask Mercedes, our first virtual assistant in the car and also outside the car. So you can utilize this virtual assistant whenever and wherever you want.
Show me.
So whatever you want to know about your car, how can I charge my telephone, what kind of drive modus am I able to choose, you are able now to simply ask your virtual cognitive assistant. But what is also now, we integrated the augmented reality for the first time in our digital product. So what you can do is, you can simply choose here, look on that, and you see, for example, that whatever you have in terms of manuals here, what to choose, what kind of button is for what type of thing, so you are able to select.
An augmented reality overlay that shows me all the main features, and then it just kind of forwarding me to screenshots and deeper explanations.
Exactly. So
that's cool.
Whether you have a question on the climate control, whether you have a question, let me say, with regards to the main functionalities, whatever it is, Ask Mercedes will be able to answer all your questions.
I love it.
So Mercedes have been going for a while now, something like 100 years. This is the first time they've ever had data from the users of their vehicles asking questions about how to use the vehicle. And good examples of the things that have come out of it are the heated front screen and heated rear screen buttons. They're almost identical. So most people don't know which one does which, so they hit both. Do we need two buttons? So for the first time, we now have the data that shows how many customers are asking that question. And it raised the point to the engineers who are responsible not only for the buttons, but the logo and the manual and the whole idea of having heated glass screens. It raises the whole question of saying, your customers are just confused. Why don't we simplify this? When the car is IC, why don't we just melt it for them? So the whole evolution now is going to go apace. So the data originally was manuals, and now it's human interaction with a dynamic manual. So from a software perspective, a developer's perspective, we now have this golden information of what are customers actually doing with the machinery or the data. I want to skip that one for time, but I also think it's worth mentioning that we're trying to do this stuff in an industrial context. So Remember I said there are some shortcuts and some tools that try and accelerate these deployments. So if you happen to be working in a factory where you need to be an expert in a machine that cost a few million and it's quite a complicated thing to operate. So we're building tools around all of these machines that give you a search capability that won't show you an elephant. It'll show you the exact page of the right manual to take the right action and safely. It'll give you an assistant on how to do it step by step, and it'll give you a peer guide. Now, the way that works is it keeps a live database of people who understand that problem and that machine. And they could be in a different part of the world, but the whole idea is to say, well, you're using your iPhone to try and solve the problem. If it was at home, you would probably push the FaceTime button and talk to a relative who could maybe guide you through it. So we're just putting those things that we're used to using in an industrial context, storing all the information, and then resurfacing the user guides to make it easier to do these things. A good example of that, and the primary point of entry for these kind of systems is visual inspection. So these phones have the most amazing high-resolution cameras and a lot of processing on them actually in the handhold. So we can now push out those visual inspection algorithms onto the phone and allow someone to look at, in this case, a line of glue and see if it's correctly positioned. So it's AI but being deployed right out there. And of course we need to know, is it working? Is the user happy? Is it coming up with a good quality result? And then feed that back in to the back end where the classifier, the piece of visual analytics software, can then be tuned and deployed for better use. I think I've got time for one more short video that will show this stuff working in an industrial context.
Hypexia, we must react to a quality alert on T9. Door panel inserts, front, left, and right.
Where were the parts produced?
Today around 10:30 a.m.
This tool is still in production on machine 1300 tons number 5.
Okay, we must stop the production and isolate the shop stock area concerned until we understand the problem.
Understood. I'm notifying the supervisor now.
Hypexia, the problem is the distortion. Any data on what may have caused this?
Since NAFI material is being used, temperatures are known to be the root cause of distortion in 85% of cases.
Okay, what is the status of temperatures on the current process?
Temperatures in a screw and hot runner are stable and within tolerance.
Hypexia, can you detect any other abnormal parameter?
There is a very slight increase of TCU water output temperature, still within normal tolerance, but not stabilizing.
What is your estimated resolution time for this type of issue?
Okay, I'll cut that short there, but you get the idea that it's discussing with her in context how to solve a problem, and I think that's pretty impressive. As a quick reminder, the key messages are that you can't really do any of this AI without the right data, without the right information and architecture being available. There are papers that you can read on the technical things that you should be doing, and there are products that you can buy, such as shortcuts, that already have starter kits embedded in them. But the primary thing here is to actually look at the business value of some of the applications that you've seen. The numbers in terms of time saving, engaging customers, increasing customer loyalty, make it absolutely a no-brainer to be deploying AI. So to align your careers, as I've done, around this 16 trillion euro opportunity to put data in a shape that will allow us in the computer industry to really entertain our end users is really what I'm doing, and I hope you guys can do the same thing. So thank you for your attention. Thanks for staying awake after a lunch like that, and I look forward to taking any questions you may have.
Well, thank you, Toby.
Thanks.